Good morning. So in the last class we have discussed the interference fringes produced by Young's double slit experiment and the interference pattern produced with white light. So we now know how the interference fringes are produced and the theory behind the interference fringes. Now we'll discuss about the Fresnel's two-mirror arrangement. So Fresnel produced the interference fringes by using two plane mirrors. With just two mirrors, he produced the interference fringes. We will discuss now how these fringes are produced using two mirrors. So here M2 is one mirror and M1 is another mirror. This line up to this point represents mirror M2 and this represents mirror M1, and these two mirrors are arranged in such a way that the angle of inclination between these two mirrors is very small. That is, it is marked as it is. I can show you an exaggerated figure of this so that you can understand what is the angle or what is exactly the arrangement. So in this book this angle is not that much clear. I will show you another picture to show you the angle or the arrangement. That is, this is mirror M1 or M2. In the previous picture, this mirror was marked as M2 and this mirror as M1. Whatever be the name, these are the two mirrors. The one side of these mirrors are polished. That is marked as this bar lines, and the angle of inclination, this is the line extended from this mirror M1 or M2, and this is the line. So the angle of inclination between these two mirrors is marked as this. This is nothing but theta, which is very small. So these mirrors are arranged in such a way that the angle of inclination between these two mirrors is very small. So I will switch back to our previous picture. We will discuss the theory with this picture. Okay, so now you can understand what is the angle or the arrangement of this mirror. So this is mirror M2 and this is mirror M1, and this is the very small angle of inclination between these two mirrors. Okay, now we have placed a monochromatic source of light here, so that a light from this source is falling on these mirrors. So light from this source falling on this reflecting surfaces of mirrors or on all the faces of this reflecting surface. So from this point to this point is mirror M2. So light will fall from all the reflecting surfaces of this mirror and all the reflecting surfaces of these mirrors too. But we have drawn only two lines, light source falling on these mirrors with two lines only at the end points. That is, one line at this end of mirror M2 and one mirror at the end of this mirror, and another line which showing the light falling on the end point of mirror M1. Okay, this is the point of contact of mirror M2 and mirror M1. So in between these two lines there are also light falling on these surfaces. Okay, but we have drawn only the end point line of light. Okay, so what will happen when light falling on these reflected surfaces? This light falling on these surfaces get reflected and will go along this line, and this light falling on this will get reflected along this. Similarly, these light sources. Okay, so we have drawn all the light sources which get reflected from this surfaces. So we have drawn all the possibilities, that is the reflecting lights here from this point here, and from this point this can be here or here, and from this point this can be this point. Okay, so the lights gets reflected, and if we are placing a screen at this point, we will get indifferent fringes between the region E and F, because this is the region of superposition of lights from the two mirrors, from the reflected light from the two mirrors. Okay, so this is the common region between the lights reflected from these two mirrors. From the first mirror it was this region, and this region, and from the second point it was this region and this region. So the common region is E and F. Okay, that is shaded with this line. So this region will be the region of superposition of light waves reflected from these mirrors M1 and M2. So if you look at this figure, you can see that the light reflected from this point is appear to come from, or similarly the light reflected from this point. Okay, so light falling on this M2, that is at the end point of M2, this point and this point. This point is reflecting through this line E, and this point is getting reflected through this line H. Okay, so the reflected lights from the mirror M2 illuminates the region EH, and the light from the source S2 is from source S on M1 at the end point of M1 is getting reflected along the line, this line at the point G, and from this point this illuminates and reaching the point F. So GF is the region illuminated by the light reflected from the mirror M1. So the common to this region is EF. So EF is the point or region of superposition of lights reflected from mirror M1 and M2, and where we will get interference fringes. And C is the central point where the distance from this point of contact of this mirrors is equal, so that this will be a central point. Okay, we can see when we discuss it more detail. That is, the light reflecting from these points, this line and this line, is appeared to be come from a virtual source which placed behind this mirrors, that is from the point A. That is, this reflected light appeared to come from this point A, and also this reflected light is appeared to come from this point A. So this acts as a virtual source. Similarly, the light reflected from this point, that is this light J, is appeared to come from a virtual source which placed at B, and also this beam of light which appear to come from this source of light B. So the light reflected from the mirror M2 is appeared to come from a virtual source A, and the light reflecting from mirror M1 is appearing to come from a source virtual source B. So A, B are two virtual sources. That means the light reflecting from the mirrors M1 and M2 seems to be coming from two virtual sources A and B, which are placed behind these mirrors. Okay, we assume so. The reflection look like, and the distance between these two virtual sources is marked as D. Okay, and these two sources are separated by a very small distance, which is small d, and this distance, since this distance is very small, this is line. This seems to be lie on a plane or line. Okay, and we will get fringes on this, bright and dark fringes on this region, CE and CF, according to the condition of bright and dark fringes. Okay, so we have marked the point of contact of the mirror M, which is marked as M, or M, to the point O, that is from the virtual source SY1, and from the point of contact to the screen SY2. And in total, this Y1 plus Y2 represents capital D, and capital D is the distance between the source and the screen. Okay, so this is the Fresnel's two-mirror arrangement. So we have actually used a source here, but by using these two mirrors in this arrangement, we can produce two virtual sources behind these mirrors, and these virtual sources produce bright and dark fringes on the screen. This is how we are obtaining interference fringes on the screen by this arrangement of two mirrors. This is what Fresnel did in this experiment. So we can discuss the theory now. So we will get interference fringes in the region EF. Okay, so we have seen capital D is nothing but Y1 plus Y2, which is the distance between the virtual sources and the screen. And the fringe width equation, we know the equation of fringe width as beta, which is equal to lambda capital D by small d. Lambda capital D by small d, where lambda is the wavelength of the light used, and capital D is the distance between source and screen, and small d is the distance between the two monochromatic source of lights. Here, this virtual source is acting as the sources here. So this is the common equation for fringe width or bandwidth. So a point on the screen will be at the center of a bright fringe if its distance from the point C is the central point, is n lambda capital D by D, where n is equal to 0, 1, 2, 3, etc. That is, if this fringe to be bright, the condition is that the distance from the point C to that fringe is n lambda capital D by small d. If this distance is such that, then it will be a bright fringe, and it will be a dark fringe if this distance from the C to that to the center of that fringe is 2n plus 1 lambda d by small d. This is the conditions for bright and dark fringes, which we have discussed in the last classes. Okay, so if the fringes satisfying these conditions, then we will, according to these conditions, we will obtain bright and dark fringes on the screen. Okay, for the fringes to be formed, the following condition must be satisfied. That is, The two mirrors M1 and M2 should be made from optically flat glass and silvered on the front surfaces. That is, we will get the interference. We have used this setup to produce interference fringes. So very good interference fringe pattern will be obtained on the screen only if it satisfies some conditions. The first conditions is the two mirrors C1 and M2 should be made from optically flat glass and should be silvered on the front surfaces. And the second point is no reflection should take place from the back of the mirrors. So the back side should be very much polished such that no reflection should take place from the back side. Back side means this portion. So this portion should be very well polished in such a way that no reflection should take place from this side. If reflection takes place from the other sides also, it will affect the fringe formation or interference. The polishing should extend up to the line of intersection of the two mirrors, and the line of intersection must be parallel to the line of source. That is, the polishing of the mirrors should extend to the point of intersection, that is the point of contact, the point of intersection of these two mirrors, and the point of contact should be in line with the line of intersection must be parallel to the line of source, that is the slit. So if these conditions are satisfied perfectly, we will get fringe pattern on the screen. Now we have seen the distance between the vertical sources is taken as small d. And it can be calculated by using the angle of inclination. That is, suppose the distance between the points of intersection of the mirrors and the source S is y1. We have already marked that y1 in the figure. Theta is the angle of inclination. Theta is the angle of inclination between the mirrors. So the angle of separation between A and B is 2 theta. That is, this is the angle of inclination theta. So this is the this line is the point of contact. So this is the line of contact of these mirrors M1 and M2, and we have shown here the angle of inclination theta, and this is the line to the point of contact. So this line where the light from the virtual source or the reflecting line from the point of contact, the extension of the reflected light from the along the point of contact, and this line, the light reflected from this line of contact by this mirror. Okay, these are, and the angle between this line and the central line to this point of contact are thetas. Okay, so this angle is theta, this angle is theta. This theta is the angle between this straight line to the point of contact and the reflected line along this point of contact. Okay, so these angles are theta. So the total angle between these two lines, that is light from these two vertical sources, are 2 theta. So we have got A, M, B. In the triangle AB, angle AMB is 2 theta. Okay. So angle between or the angle of separation between A and B is 2 theta. So now we have got The separation between A and B is D, and separation between A and B in terms of angle is 2 theta. Now, if we draw a circle with center as M and this as radius, so this virtual sources will in such a way that the virtual sources and the monochromatic source of light come on the circumference of the circle, we will get an arc like this. The circle can be completed along this. Okay, so this point, this line OM will be the radius of the circle. Similarly, OS will be the radius of the circle. So we are drawing a circle with this as radius such that the monochromatic source of light and virtual sources are lying on the circumference of that circle. So here OM is the radius. So we know this point is, so that OM, BM and AM etc. are the radius of this circle. Okay. So we know the angle between these A and B is 2 theta, and this separation between A and B is D. This can be treated as a straight line because these points are very close to each other. So this is almost planar, almost lying in a line. So that from the relation between the angle between the radius and the arc length, we will get small d is equal to 2 theta into y1, where y1 is the distance between this point and this point of contact. This is nothing but, that is, this is equal to the radius. So this is nothing but y1. So we will get small d is equal to 2 theta into y1. So when the we have got d, and from this so once we know the value of d, we can calculate the fringe width. Okay, we know the wavelength of lambda and the distance between the source and the screen, so that we can calculate the fringe width according to the condition of constructive and destructive interference. So this is how the Fresnel two-mirror arrangement produced interference pattern, and this is a theory of how we are determining the interference fringe width. So if you are using white light instead of monochromatic source of light, the central fringe is white, because where all the light will constructively interference, all the wavelength will constructively interfere here, so white point will appear at the central point C. Whereas on both sides of C, on above C and below C, we will get colored fringes that we have discussed in the last class, that is interference with white light. This is the same theory here. Colored fringe, because the fringe width beta depends upon the wavelength. Only the first few colored fringes are observed and other fringes overlap. Therefore, the number of fringes seen in the field of view with a monochromatic source of light are more than with white light. So we can see more fringes with monochromatic source of light than white light, because as the distance from the central point increases, the other fringes overlap. So we can see only first few colored fringes. Okay, so this is about Fresnel's two-mirror arrangement in order to produce interference fringes.